Welcome back to 320A. This is the last lecture scheduled, but there is a review session in 2 days if you want. I already have a room. It won't be this room. It will be Harville, room 204, and it will be at 3 o'clock on reading day, which is about 48 hours from now, but not quite. It's a little less than that. So 47 and a half hours from now, we will have our review session for the final exam. The final exam is not on a Tuesday or a Thursday. It's on a Wednesday, and it's on the 8th. It will be in this room, and it's from 3:30 to 5:30. It will be a 2-hour exam. It will be comprehensive, and there's more than one practice final exam available now. There's a more recent final, one from fall of 17, and there is a problem on there that we didn't talk about in this class. You won't be responsible for that particular problem, which was dealing with two-port networks. I'll give you another one based on the material that we have covered this semester, and you should find a topics or a list of outcomes that you should be ready to work towards or demonstrating your competency at on the final exam. What have I not addressed? Homework number 9 is due today. Homework 10 is due on that reading day. Question? Test will probably be multiple choice. The question was, will the final exam be multiple choice? And my answer is it probably will be. Yes. You get note sheets, so that's one of my goals today is to talk about the final exam. But there is partial credit possibly on the final, so show your work. There are some questions that are some answers that are more valid than others. There's obviously a correct answer, but there might be another answer that's part of the way. So maybe you made a sign error, and I've included that answer as one of the answers, but at least you won't get no tests or no points. You'll get some partial credit. So show your work so that I can see how you are arriving at your final answer. So if it's worth 10 points, maybe you'll get 5 on particular. I'm not sure I'll get that detailed on the partial. Somebody said, or 8 points, or, well, I don't want to identify students because this is being recorded. Yes? So what if you get the answer right and don't show any work? You will get 0 points because I know that you're looking at seat number 3's answer. No, so it's multiple choice. So it's on you to give me, if you get the correct answer, then it's the correct answer. Pardon? Do I have none of the above? I don't know if I'm going to have none of the above. Yeah, you're giving me a lot of good ideas. You can ask me more detailed questions all week. I'm having additional office hours. Tomorrow is Wednesday, which is the last day of class. This is your last day in this class. But tomorrow's office hours are the same as normal since it's still the last day of class. And I don't even remember when those are. I think 11 to noon on Wednesday. Thursday, it's the normal time, and then after that, these are additional times, and the Thursday time is during reading day, so that's beyond the normal semester. But, I guess Thursday, it doesn't matter to you. You'll be finished, but my other class, that's for their benefit. They have a final exam on Thursday. All right. What do we want to do today? Here are our goals, not very many, and it's typeset. But if we don't get through all of this, I will give you supplements. on D2L. You guys are getting good at taking those supplements, and these are not banned supplements. These are good supplements for you to be taking. But first we'll talk about the final exam process. I will show you basically figures from the book on the different ways that you can realize these types of filters with an op-amp based circuit or with active filters. Then we'll talk about frequency scaling. And that you can sort of think of in two different ways. One is, how do you scale the circuit parameters, the R's, the L's, and the C's, if you want to do magnitude scaling by the impedance or frequency scaling. And those are actually your final results, R1 being the initial value and R2 being the final value in your circuit, likewise for L's and C's. Or if somebody hands you a transfer function that's maybe a normalized transfer function, and a lot of times we deal with those, maybe it's normalized to have a bandwidth of 1 radian per second, and we don't all live in a 1 radian per second filter world. Sometimes we want that to be something else. How do you frequency scale a transfer function? And this is really what you do. You take your normalized transfer function, and everywhere you see an S, you replace it with S over K sub F, where K sub F is your frequency scaling parameter, and that is related to your old frequency by this relationship. K sub F times S old gives you S new. So if you wanted S new to be 10 radians per second and your normalized filter had a bandwidth of 1 radian per second, you would use a K sub F of 10. Now if somebody says, oh, I want my cutoff frequency to be 100 hertz, well, then you have to include this 2 pi relationship, but S old is probably still 1 radian per second. And now you want to do S new, which is 2 pi times that 100 to get your scaling factor K sub F. We will then talk about higher order filters, and sort of your instant response might be, well, I have a first order low pass filter and I want a second order. Let me just put those together. Let me cascade them, combine them. And we'll show that there's a drawback to doing that. That actually decreases your cutoff frequency or the bandwidth of that filter by just simply stacking those identical elements together. And that is trying to then motivate the benefit of the Butterworth pattern. The different pole patterns associated with the Butterworth keeps your cutoff frequency at a value of minus 3 dB no matter what the filter order N is. So if you want a 10th order filter, if you use the Butterworth pattern of poles, you're guaranteed that your 3 dB frequency is still 1 radian per second. It hasn't shifted down to a lower frequency. That's how we will address the higher order filters. We'll simply look at how you combine. So filter orders are obviously integers. N equal 1, N equal 2, N equal 3. How do you build those? Well, you just separate those. If you have a fourth order filter, you put 2 second order stages together. And there's a table, I don't know that I stated it here, but table 15.1 gives you the factored form so that you know how to allocate those parameter values to achieve the particular pole locations in the Butterworth pattern. If you had a fifth order filter, you would have 2 second order stages and 1 first order stage. It's easy to combine. You just have to learn how to create those second order stages. They aren't identical. They are structurally the same. It's just your L's and or your R's and C's are different values, and that's based on table 15.1. We'll introduce how to design. If you now say, oh, I want a really sharp roll-off in my stop band, well, what's my filter order? We'll give you a formula for that. How do you find little n? Oh, my filter order needs to be 7. Oh, my filter order needs to be 3 to achieve this particular steepness of the roll-off. And you know how steep you're falling off in the stop band based on the order of the filter. If you had a 6th order filter, how fast are you rolling off in the stop band in terms of your magnitude? What's your magnitude slope? If you have a 6th order filter, low pass, you have minus 20 dB per every N, don't you? So N, if I said that was 6, you have 6 times minus 20, you have a roll-off of minus 120 dB per decade. That's pretty fast. Okay, 6th order. That gives you a pretty sharp transition from your pass band to your into your stop band. If it's a 3rd order filter, you're going down at minus 60 dB per decade. Then I'll give you low-pass Butterworth filter design in 6 steps, 6 easy steps. And again, we may not get to all of this, but I'll give you this as little pieces in supplements, notes, and video. Oh, you don't want the pieces? Is that what that meant? And then I'll give you an example, 3rd order low-pass filter design. Unless you don't want it, I can keep it. But I want to be sharing and giving, so I will provide it. Here's the process for the final exam. Again, it's in this room on Wednesday. What time? 3:30 to 5:30 on Wednesday. 4 sheets of notes, front and back. And you need to include on those 4 sheets your transform tables or operations. Make that a part of your 4 sheets. That's the columns that have your time domain and frequency or Laplace transformed relationship. Shift happens, so remember those sheets. Shift is the Laplace, right? Shift key. Capitalization. You can bring a straight edge and a protractor if you want to sketch your Bode plots. Something to write with, your calculator, but the others are no's. You do have practice finals, and I've provided the answers, I believe. Maybe not the solutions, but the answers. There's a list of topics, and then I will provide the review lecture that happens on Thursday at 3 o'clock in Harville 204. And it's this Thursday. Yes, if it's next Thursday, a day late and a dollar short for this class, right? So it needs to be this coming Thursday. Active filters. This is sort of just sliding through, kind of trying to see what these look like. Here is a 1st order low-pass filter that's created from an op-amp. It's active. What you're not seeing are the power supplies that have to energize this. That's what makes it active. It does have negative feedback, but you know how to derive the transfer function for this op-amp circuit. And that you can show gives you this low-pass filter frequency response. That would be a good review to just try to derive those transfer functions for these types of filters. And you can kind of compare these to each other. This now gives you a high pass behavior. Now we're coming up from the bottom and we go flat after a cutoff frequency. And now your R and C are in series, and that gives you this 0 at the origin to get you coming up from behind or from the bottom, and then you roll off with your pole. You can combine those two pieces. Here's a low-pass filter. Here's a high-pass filter in cascade, which is what this block diagram is showing you. And if you wanted to change the sign, you could put an inverting filter at the end or at the beginning, and there now gives you this bandpass filter where you're passing a particular band of frequencies. Yes?
Would you just multiply each of the transfer functions in the frequency?
So essentially the question was, do you multiply the transfer functions in the frequency domain? And the block diagram, that's what that's showing you. That's true. That's how you achieve this. Now there are certain relationships on the high pass and the low pass parameter values. You're not held responsible for this on the final. We're not going to be designing bandpass filters. We will be doing focusing on the low pass filter. But this gives you needed information when you finish this class. If somebody says, oh, I need a bandpass filter, you now at least appreciate what might be needed. You can combine them in another way, now in parallel, and produce a band reject filter. You now have a low pass, you have a high pass, but now they are doing that differently. Here's your low pass, then here's your high pass, and they're notching out a particular frequency. See what all you can do with all this material? It's amazing. It's fun, isn't it? So now let's figure out how we can scale these nominal or these normalized transfer functions, because that's really what you work with. Is you start with a third order filter that's maybe has poles that have natural frequencies of 1. And not everything we do in life has a natural frequency of 1 radian per second. We need to scale it, and we may want to scale its impedance, because maybe Josie has a bunch of 10 microfarad capacitors, and you have to design your filter so that you achieve that. So here is now how we can scale in terms of frequency. That's what we're calling K sub F, and magnitude, which is what we're calling K sub M. So let's first look at scaling the impedance, or magnitude scaling. Subscript 1 is the initial value. That's the normalized frequency, or the normalized transfer function. Subscript 2 is the final value. So when we talk, or if we have something with subscript 1, R with subscript 1, or L with subscript 1, those are the inductors or resistors in our normalized system or circuit. Here's our first goal. We want to now do magnitude scaling, which says that we want our final magnitude to be scaled from the initial impedance. And that means, how do we change our resistors, our inductors, and our capacitors if we want all of their impedances now to be modified by this non-negative scaling parameter K sub M? What's the impedance expression? This is really challenging for a resistor as a function of omega. That's just R, isn't it? So now if we have our impedance of a resistor is R, and we want to now magnitude scale such that we say, okay, Z sub 2 is equal to K sub M Z sub 1. Well, what is Z sub 2? That's just R sub 2. K sub M is K sub M, and what's Z sub 1? That's R sub 1. So if you want to change your impedance by 100, K sub m is 100, and if R1 started out being 1, now your resistor has a value of 100, K sub m times 1, in your new scaled system or circuit. What about the impedance of an inductor? What's its expression? That's SL, but now we're doing it with omegas. So now we replace S with J omega, and this is now J omega L. We now have J omega L for an inductor, and again we want to have our final impedance a scaled version of our original impedance, but now we replace these Z1s and Z2s with what they are equal to based on the impedance formula of our inductor. Z sub 2 then on the right says that we have J, what? That's Z sub 2, is just J omega L sub 2. And that's equal to K sub m times Z1, which is J omega L1. And we're trying to find a relationship between L2, K sub m, and L1. The J omegas can be divided out in that relationship. And now you see how to modify the value of your inductor. Again, it's weighting the original inductor's value by this magnitude scaling amount, K sub m. It's consistent or similar to how we scaled our resistor. What about the impedance of a capacitor? That's 1 over J omega C. And again, we want to do our final impedance, Z sub 2, needs to be a scaled version of the original impedance, Z sub 1. We can now say, oh, this is 1 over J omega C sub 2. And that's equal to K sub m times 1 over J omega C sub 1. We could multiply both sides through by J omega, or those cancel. And we can now push that around and solve for C sub 2. C sub 2 is now C sub 1 divided by K sub m. Meaning, if you want to scale your capacitor in your new magnitude scaled circuit, you divide by that K sub m factor on your original capacitor's value. What if we do frequency scaling? We just did magnitude scaling. Now we want to do frequency scaling, where we want the impedance at the final frequency to be the same as the impedance at the initial frequency. Now we're trying to, basically, this is sort of what we do to move the bandwidth around, and we may use the magnitude scaling to utilize the parts that we have on our bench or on our available to us. So here we want our impedance at the final frequency, Z sub 2, to equal the impedance at the initial frequency. And let's just say that we're scaling our frequencies by K sub f. We have omega 1 times K sub f is equal to omega sub 2. If we had a normalized frequency omega 1 of 1 radian per second, and we wanted omega sub 2 to be 1,000, K sub f is 1,000. So now let's just repeat what we did before with the R's, the L's, and the C's. What's the impedance of a resistor is R. So now we want to relate that frequency-wise. Does R depend on frequency? No. So here we don't need to worry about changing our resistor values when we're frequency scaling. This just says that if we want the final impedance to be equal to the initial impedance at the two different frequencies, and since Z sub R doesn't depend on omega, we can just use R2 as the same as R1. That's not going to be the same for the others because they obviously depend on frequency. L, Z sub 2. This now is the impedance at the new frequency. This is now J omega 2 L2. And we want that to equal, or maybe what I should do is at least get rid of that omega 2. We know how it's related to omega 1 by this frequency scaling. Or we can now rewrite this as J times K sub F omega 1 L sub 2. Because we know that we want to scale our frequency by that relationship. We want omega sub 2 to be a factor of K sub F different than omega 1. But we also said that we wanted Z2 and Z1 to be the same at the two frequencies. And what's Z1? It's now J omega 1 L1. And what we're trying to do now is compare this with that to come up with a way that L2 needs to be determined based on L1 and this frequency scaling parameter K sub F. So now we can cancel the omega 1, we can cancel the J, and solve for L sub 2. L sub 2, or maybe let me just say K sub F L sub 2 is equal to L sub 1, and that now allows us to say that L sub 2 is L1 over K sub F. This scaling parameter obviously enters reciprocally to how the magnitude scaling came in on that inductor. So if you're doing both, if you're doing magnitude scaling and frequency scaling, we'll combine them in just a minute. The magnitude will be upstairs, the frequency will be downstairs in terms of the scaling factor. But before we combine them, let's just look at our capacitor. C, Z sub 2 is 1 over J omega sub 2 C sub 2. Doing what we did before, let's replace omega 2 with its connection to omega 1. That's K sub F omega 1, or we now have 1 over J K sub F omega 1 C sub 2. But we want Z sub 2 to equal Z sub 1, and Z sub 1 is 1 over J omega 1 C1. The numerators are the same, so really we just need to equate the denominators to establish the connection between C1, C2, and K sub F. The J's can be removed, the omega 1s can be removed, and now we can see that K sub F, C sub 2 is equal to C1, or C2 is now C1 over K sub F. And if we combine the magnitude scaling and the frequency scaling, we get the following. So the two scalings can be combined, meaning R sub 2, what's the new resistor value with magnitude scaling and frequency scaling considered? So now it does depend on the magnitude scaling, but frequency scaling doesn't influence the resistor. This one now is going to be K sub M R1. L2. Now if we look at how we would, here it's reciprocally related to K sub F, but it went in upstairs on K sub M. Combining that now says that L sub 2, if we're doing both together, is going to be K sub M over K sub F times L1. And finally, C sub 2, they both came in downstairs. C1 divided by K sub M, K sub F is how you would find the final capacitor value given the initial and these scaling factors for frequency and magnitude. And because of time, I'm going to say, I'll give you an example of this offline, of how you can design a first order filter to maybe have certain values of capacitors and have a given bandwidth on that low pass filter other than 1 radian per second. That's now how we would scale parameters. What if somebody gave you a transfer function and said, I want you to scale this in frequency to have a different proper bandwidth. So now let's look at scaling. Transfer functions. It's like we did before. Suppose now that we have omega 1 is our initial frequency and omega sub 2 is our desired bandwidth or frequency, and we want to use this same scaling parameter K sub F. Well, if we're dealing with transfer functions, a lot of times those might just be written in S's. So now let's say that we are going to say, oh, S sub 2 is now K sub F S sub 1, where here is our initial variable S in our, let's say, normalized transfer function, and S sub 2 is our final. And one way that we will actually do this is we may have a normalized frequency that's in terms of our initial S. Well, S is actually equal to S2 over K sub F, and that's how we could now scale. We could replace all of our original S's in our expression with S over K sub F, and now we've scaled in frequency. So let's see how that plays out. Let's frequency scale a normalized transfer function. Suppose the final transfer function is what we call h sub 2. Well, h sub 2 of s is going to be our normalized transfer function, h sub 1 of s. And here, if we wanted to, we could say, okay, that's going to be s sub 2, and here's s1. But we need to now replace s1 with s2 over k sub f. And that's the process that we would use. If our original normalized transfer function was sixth order, we might have s to the sixth, s to the fifth floating around. We just say s to the sixth is now going to be s over k sub f, and we're going to raise that to the sixth power. Or if it's now to the fourth power. So let's look at an example. Suppose we let our starting transfer function h sub 1 of s be 1 over s plus 1. And now you can go on and about this particular transfer function as far as what it is, right? Where is the pole? So we could call this a normalized transfer function with pole at s equal minus 1 radian per second and our cutoff frequency omega 1 equaling 1 radian per second. If you had to sketch the Bode plot of this, you should be able to do that. It's now 0 dB until at 1, and then what do you do at 1? Now you go down, because you're in the denominator is where your factor is. It's a pole factor. You go down based on that 1 factor, and you're going down forever at minus 20 dB per decade. What's the phase curve look like for this? What's the phase curve of this look like in the Bode plot? Is it constant? What's the angle of h of j omega as a function of omega? So you'll have to do this by tonight when your homework is due, but this is now, what's the angle of this when s is tiny? Or you're now replacing s with j omega, and you say j omega, omega is small. What's the angle of 1 over j small plus 1? 1 plus j small is 1, isn't it? The denominator is basically 1. What's the angle of 1? So now you're looking in the complex S-plane and you say, oh, there's 1 if I'm standing at the origin and I'm just looking out and I see 1. I say, well, how much of an angle do I have to look through? Nothing. And it's 1 away. It's 1 at an angle of 0. That's the denominator. So you have 0 degrees being contributed by this transfer function for low frequencies. And what's low frequency in this example? It's relative to the cutoff frequency. And low, we usually say, well, you look at all of your poles and zeros, and what's the lowest one? And then you go back a decade and say, okay, nothing's happening in our straight line world before a decade before all of these breaks occur. In this case, a decade below 1 is 0.1. Low frequencies are any omegas less than 0.1. And we have an angle of 0 degrees up until that frequency. What's high frequency in this example? Oh, I'm sorry. What's the frequency that's considered high frequency in this example? A decade beyond the break, and that's 10 in this case. So if you looked at, if you're standing in the complex S-plane on that pole, which is at S equal to -1, and you say, okay, the positive reference point for my angle is pointing off in the positive real line direction, and now I need to look up the j omega axis to J10. What's that angle? It's pretty close to 90. So we're just approximating it as 90 degrees. But it's downstairs, so it really contributes minus 90 degrees to that transfer function. The angle of that pole is 90, but its contribution, because it's in the basement, is minus 90 degrees. So we are at 0 degrees until 0.1. Then we're minus 90 degrees after 10. And the straight line approximations, we're just connecting those two limiting values with a straight line, and it passes through minus 45 degrees at the break frequency, and that's exactly where this goes through in reality. If you evaluate the angle of 1 over j omega plus 1 at omega equal to 1, the bottom term is going to be a complex number, 1 plus j. That has an angle of 45. It's downstairs, so there's the minus 45. Where was I going? I was trying to illustrate how you can tell me all sorts of information about a transfer function that looks like 1 over s plus 1. What's the DC gain of that transfer function? Okay, by the final exam, we all better be singing in unison. The DC gain of that transfer function, now what are we doing? What's DC in terms of S? 0. We plug in S equal to 0, and what do we get? 1. So it's 0 dB, the magnitude. So it's 0 dB, but the actual value is 1, so that what does that mean? You inject a cosine of amplitude 10, and what's close to DC? Well, it's lower in frequency than 0.1 in this example. So if you had cosine of 0.01 t, you're basically seeing that same amplitude at the output in the sinusoidal steady state. Question? Yes.
So I should plug in the S that's considered very low?
So now if I ask for, the question was, do I plug in a value of S that's really low? If I'm asking for the DC gain, I'm asking for omega equal to 0. Oh, well, omega equals 0 is as low as you can go. But where is it on your Bode plot? Where is DC? On the Bode plot, where is 0? You can't get to it, can you? Because it's a log frequency, it's a log axis. So you get to 10 to the minus 2, 10 to the minus 3, 10 to the minus 4. You never get to 0. You just get to very small values. And that's why you could say, oh, look at small values, and that's my DC gain. Now, if I had a pole at the origin, I wanted to cover up that constant 1 in the denominator, then it's a little different. Then our gain at DC, it's infinite, isn't it? It's really unbounded. All right, so suppose that we now want the following. We were talking about frequency scaling. Let's say we want our scaled frequency to be 5 radians per second. And that now immediately tells us the relationship between omega sub 2 and omega sub 1, or we can now find k sub f. So with omega sub 2 equal to k sub f omega 1, we now have k sub f. Our frequency scaling factor is 5. Or we could say, depending on how you want to think of this, you could say your new scaled frequency, S new, or we were calling that S2, is K sub F S1, or that's K sub F S old. Yeah, it looks like it's sold, but we're not having an auction, so this is now just going to be S subscript OLD. It's not sold. You can sell whatever you want after the final exam, but here you need to know that it's S sub new over equal to K sub F S sub old. So that now, if you needed to get rid of S sub old in your normalized transfer function, you now say, oh, that's going to be S new over K sub F. Really, your strategy is as straightforward as just replacing S in the normalized filter with S over K sub F. So that if you now want H sub 2 of S, that's now H sub 1 of S over K sub F. And for our first order example, S was just by itself downstairs, so we replaced that with S over K sub F, and in our example, K sub F was 5. And if you wanted to clean that up a little bit, you could say, let me scale it top and bottom by 5. But right now, it's in time constant form. And can you see the DC gain? DC gain is 1. Now if you write it in pole 0 form, that's equivalent, isn't it? I haven't changed the transfer function. It's just been rewritten by multiplying by 1, where 1 is 5 over 5. And now I have 5 over S plus 5. What's the DC gain? 5 over 5. It's not 5, is it? It's 5 over 5. Now, what can you tell me about that transfer function? Can you tell me anything about the bandwidth of H sub 2 of S? The pole's higher, isn't it? We scaled it. So we've now moved that pole from S equal minus 1 to S equal minus 5. And that was pretty easy, wasn't it? We started with a normalized transfer function that we were happy with. We liked its properties. We just needed to move its frequency to a new value, and we said, let's move it to 5. So now we have a cutoff frequency here in H sub 2 of 5 radians per second. Suppose now we know how to scale, and we want to do more than just scale first order filters. We want to build things that roll off more steeply or have sharper cutoffs. We want higher order filters. Now I want to try to justify why we want to use Butterworth filters and not just combine these first order filters like H sub 1 and saying, oh, well, I just need a fourth order filter. Let me say 1 over S plus 1 raised to the 4th. I now have 4 poles at S equal to minus 1. That's not going to be quite what we want, because now our cutoff frequency will be a lower frequency. What? So let's see where that comes from. Let's talk now about higher order filters. And what I tried to motivate this discussion was with a warning. So now here's a yellow label tag somewhere going into the final exam. You have a warning. If I now say design a fourth order filter, you probably don't want to use 4 of those 1 over s plus 1s. You probably want to use a Butterworth with 2 second order stages. So here's the warning. Creating a second order filter by cascading, that's just meaning putting the output of the first one into the input of the second one. That's the cascade, a series connection of these. Creating a second order filter by cascading 2 identical, and that's the key phrase that is why we have the warning, first order filters does not preserve the cutoff frequency. Our cutoff frequency is not omega c equal to 1 when we get higher than n equal to 1. So and now you have the skills and the tools to explain this to yourself. So let's just walk ourselves through it. Here's an example. Suppose that we start with that. That one we feel very comfortable with. We like it, don't we? 1 over s plus 1. We could write a book on this one, right? So if somebody now is in an interview and they say, tell me about a low-pass filter, and you go, okay, how much do you want to know? Let me start. And you start with this. And you could draw a RC circuit with this. You could actually draw an op-amp, an active low-pass filter, and show them how the R's and the C's are related to give you a bandwidth of 1 radian per second. So this is now an abridged story is just to say the following. Well, here is a normalized first order filter. Well, it's a low pass with a pole at s equal minus 1 radian per second. And you could even pull out the S-plane and sketch that. You could put a pole there and say, oh, you stretch this rubber sheet on it and you have a tent that's been on the mall most of the semester, and you can find the frequency response based on the height of that tent. And this now gives you a cutoff frequency of 1 radian per second. Now I ask you, what's the magnitude of h of j omega when omega is equal to 1? What's the actual magnitude of h of j omega when omega is equal to 1? And you go, I had complex numbers in middle school or wherever you have it now. Okay, maybe you didn't. Maybe you didn't have complex numbers in middle school, but you had it in 220, right? ECE 220. I think Dr. Marcelin started from day one with complex numbers, so you'd be very comfortable with them in 320. You still have the scars to prove it. So let's evaluate this. What's this look like? Well, we just take the magnitude of a complex number. 1 over j omega plus 1, and we're letting omega equal to 1. So this now, the magnitude of a ratio is the ratio of magnitudes. So I can now say, I need to find the magnitude of the numerator and divide that by the magnitude of the denominator. What's the magnitude of 1? This is challenging, I know, but we're kind of loosening up for the final, right? So this is now 1. And how do I find the magnitude of the denominator? Magnitude, this is just Pythagorean, right? This is just the square root of real part squared plus the imaginary part squared. And those are easy to square, aren't they? 1, I can square 1. So now we have the square root of 1 squared plus 1 squared. Or, this now becomes 1 over the square root of 2. That's the actual magnitude of our first order low pass filter with a pole at -1. And does that make sense? Or, can you now tell me what the magnitude is in dB at the cutoff? Well, all we have to do is find 20 log of this, and that's our magnitude. So now we have 20 log base 10 of 1 over the square root of 2. And if you had complex numbers in middle school, you probably had logarithms in 3rd or 4th grade, right? I think they waited until at least 1st grade before you started having logarithms. But now we have logarithms, and you know the properties of logarithms. We can now say that this is the same as 20 log of 2 raised to the -1/2. Yes? We have the square root is 1/2, and it was in the denominator. There's our minus. And now that exponent can come out front of our log. Or we can say, oh, this is now equal to -1/2 20 log base 10 of 2. This is roughly 0.3. We now have -10 times 0.3, or we are now at -3 dB in actual value in dB at the break frequency. And that's what we knew. We knew for that first order filter, our straight line approximation, we're 0 dB and then we start going down. But the actual curve is 3 dB below that. So this is fine. This is what we want. But what happens if we combine two of these? We say, well, we like this, but I want more filtering. I want a sharper roll-off into the stop band. And we'll get it if we put two of these together. We'll be going down at 40 dB per decade. So let's see what else happens. So now suppose we create a second order filter by combining two HFSs. And remember, we have our warning somewhere. So we're kind of on alert. Right? So let's call this H try. I don't know what that is if you put the TRY with the H. Like you were trying to do sold with S and old, but now we have S. But this is S or H sub try. Okay? And what is H sub try? This is now H of S. We're cascading these, so we're just multiplying the transfer functions together. And that is really just that. 1 over S plus 1 squared. Or if you wanted to sketch this in our Bode plot, straight line, you could do it. It's 1 over the factor S plus 1 in the denominator times S plus 1 in the denominator. You have two first order factors and you know how to combine them. But now let's look at, well, let's just say what we have. This is now a second order, which we've accomplished one of our objectives. We know this is rolling off more rapidly into the stop band. This is a second order. But now what we have to be careful with is now this has two real poles at S equal -1 and S equal -1. They're on top of each other. They're right at S equal -1. That is not a Butterworth pattern. Just telling you. Okay? That one's not going to give you a maximally flat passband. And my question now, I guess I've already given it away, is the minus 3 dB frequency omega equal 1 radian per second? Well, if I hadn't been telling you all day that it's not, you might be inclined, well, I have two poles at -1, and that's kind of what I had before with the first order. I had everything happening right at the break. Now what's going on? Well, we're rolling off quicker into the stop band at lower frequencies. Let me first say the answer is no, and let's look at the magnitude of H trie at 1 and see if it's less than 1 over the square root of 2. And if it is, then we know our 3 dB frequency is at a lower frequency, since we're lower at 1 than we were with the first order filter. Or we now say we have 1 over J1 plus 1 squared. And this isn't hard to do based on what we now have done before. We take the magnitude of the top and square it, and divide by the magnitude of the bottom and square it. Or this is 1, and here's 1 squared plus 1 squared, but we're squaring that. So the square root gets removed by the square. So now we have 1 over 1 squared plus 1 squared. Is that 1 over the square root of 2? No. So now what's it in dB? Just for kicks, we now have 20 log base 10 of 1/2. Am I doing that right? And we know what this is. But now how are we scaling it? We're scaling it with -20 times 0.3. We're now at -6 dB. We're sort of twice as far down in this dB scale at the same frequency. And what I would say or suggest now, I know you're just going to run home and just start flipping through the book and saying, man, this is fun stuff. Let me just find this and read and study about it. Look at figure 15.16. And is this the figure? This is the figure. So I'm even going to save you. You don't have to really strain to get home to see this. Here's our first order filter, and where is, well, you can't see the omega equal to 1. Here's omega equal to 1. Is right here. So the yellow highlight is omega equal to 1, and you can see that the -3 dB point is right where, these are the actual curves, where we have our first order. But then where is our second order? That looks about right. That's -6 dB. But where does that second order have its break frequency if the break frequency is the -3 dB? It's right there. And what's that? Well, that's 2, 3, 4, 5, 6. 0.6 instead of 1. Do you see how we've now sacrificed our cutoff frequency by just putting these first order sections that we shouldn't be doing together? We put another one together, we put a third one, and we're even lower. Put a fourth one, And look at it, that magnitude at the cutoff frequency. So that's not what we want. We actually want, if we increase n, if we make n 4, we would still like that magnitude to go through minus 3 dB at 1. So we want all of our transfer functions, no matter what the order, to have a magnitude at 1 when they're normalized to be 1 over the square root of 2. And that's going to require that we have this Butterworth pole pattern. And you guys now know how to find the Butterworth pole pattern. You've been to the grocery store since we last met, and I'm sure you've gone into the syrup aisle and found Mrs. Butterworth, and you said, yeah, we have a maximally flat filter. Right? And yeah, security comes and asks what you're doing with Mrs. Butterworth. And saying, maximally flat. Okay, table 15.1. What is that? That's this. This looks right. S plus 1. For n equal 2, that's not S plus 1 quantity squared, is it? S plus 1 quantity squared is S squared plus 2S plus 1. Here it's S squared plus the square root of 2S plus 1. And if you found where those poles are, they're going to be complex conjugates. They're going to be a distance of 1 away from the origin. But now they're going to be, if you're looking into the, which way are you guys? Okay, so this is your left half plane. They're going to be at 45 degrees. For n equal 3, you do have a real pole. It's at s equal to minus 1. But this is not the same as that second order factor, is it? Now you're 60 degrees up from the real line, plus and minus 60. And look at the fourth order. These are not two identical factors. What do those factors look like? Well, here's what they look like. Here's the first order. Here's our filter order, n equal 1. Here's how those poles are separated. So we now have this complex plane, and we split this sort of unit circle into 180 degrees, and you say, okay, let me make this so that I have complex conjugate pole pairs, and half of my poles are on the left half plane, and the other half are in the right half plane. For n equal to 1, I'm saying I have two poles, and they're separated by 180 degrees. And the only way that I'm going to have complex conjugate pole pairs is for them to be real in this case, and they're going to be on the real line. One at minus 1 and one at plus 1, and I'm retaining only the one in the left half plane, which is stable. What happens when little n is equal to 2? A second order filter. Now we have these poles. How many poles do we have? 4. But we're only going to keep the two stable ones. We have 4 poles that we're spreading around this circle, and they're going to be separated by 90 degrees. But in order to get them so that you have half of those poles in the left half plane and the other half in the right half plane, you can't have any real poles. Do you see that? And the ones in the left half plane, they make an angle of 45 degrees from the real axis. And that's actually where you would have the roots of that s squared plus the square root of 2s plus 1. They are now going to be, this distance is 1, this angle is 45, so you can calculate the real part and the imaginary part of those two poles. Cosine of 45 is the real part. Sine of 45 is the imaginary part. What about S equal to 3? I'm sorry, N equal to 3. Now we're dividing by 2N. 2 times 3, or 6. Now our poles are separated by 60 degrees. And we need to rotate those so that half of the poles are in the left half plane, the other half are in the right half plane. And now, since it's odd, we do have another pole at 1, at S equal to minus 1. They're 60 degrees apart, so these two complex poles are not in the same location as they were when N was equal to 2. Now they're 60 degrees off of the real line. And where are they? Well, in factored form, those are in table 12.1. You could find the roots of S squared plus S plus 1, and they're going to give you those two complex conjugate poles. What about with N equal to 4? Now we have 360 divided by 4, that's 90. Divide that by 2, it's 45. These poles are now separated by 45 degrees. This is maybe an ugly picture, but hopefully it's labeled so that you understand what's happening. Now we have to shift those 8 poles such that you have 4 of them in the left half plane, and those are the ones we're keeping in our Butterworth filter. We don't have any real pole because we're even. N is equal to is even. We now can find those. These are all a unit distance away from the origin. We know the angles, and we could find their real part and imaginary part. Or you could go back to table 12.1, I'm sorry, 15.1, and now you can see why these two quadratic polynomials don't share the same coefficients. Because two of the conjugates are fairly close in angle to the real line. They're 22.5. And the other two conjugates are 22.5 away from the imaginary line. Question?
So if the original first order transfer function was 1 over S plus 2, you just make sure that each of these poles are 2 away from the...
So now the question was, what if the original transfer function was 1 over S plus 2? Where's the pole located there? 1 over S plus 2. Minus 2, right? So now we've scaled it by 2. So if you wanted to think that way, you could say, let me just expand this Butterworth pattern by a factor of 2. You're going to preserve the angles, and now you just have to scale them by 2. So you can do the scaling either graphically or with the transfer function analytically. You can now figure out how to scale those with your parameters as well. You have the parameter scalings with the R2s, the L2s, and the C2s. Other questions? Well, here's how we put all of these pieces together. We have Butterworth filters. We want this flatter passband so that we have all of the orders going through minus 3 dB at omega equal to 1. And the strategy to building these higher orders is to play with just 2 different filter stages. A first order, which you know, that's figure 15.1, and we started today's class with that one. That has an RC in the feedback path and an R in the input line of your op-amp active circuit. And then you have figure 1521. That's a second order filter. And what you now need to do is figure out how do you find the parameters in that circuit to assign those coefficients to be consistent with the coefficients in table 15.1. What if you wanted a third order? Then you just combine a first order with a second order. Pardon? I'm serious.
No, in series.
Oh, in series. Okay. Sorry, I heard serious. I'm trying to be serious for a change. So yes, in cascade or in series. And if you wanted a fourth order, I think you can guess. 2 second orders. But these look different because their coefficients have to be slightly different. I'll give you some supplements so that you can figure out how to find little n and how to do this for a third order filter. How to pick all the R's and C's. Yes?
For a fifth one, did you have another one in series?
So now for a fifth order, that's why I said etc. Now you would take this picture for fourth order and you would add a figure 15.1, a first order filter, either at the front end or the back end. It's in series or it's cascaded, it doesn't matter. And then if you wanted n equals 6, you would have 2 of these second orders plus a third second order, etc. So you'll be expert filter designers by the final exam. I will see you, if you want, at the review session Thursday in Harville 204 at 3 o'clock.